get my notification this morning about the survey. So please fill it out so that students in semesters after you can enjoy some cookies too. That's kind of how it works. so whether you liked it or not, provide some feedback, and that will ensure that we keep doing the same. So anyway, also feel free, just a reminder, it's on syllabus, but there is a link for any kind of feedback about the class that you can follow and provide anonymous feedback, or just, walk into my office. Sometimes it's easier to just type something. Alright, so second, before I forget, we will post first homework tonight. So we just need to do some final check on the homework, which we will do after the class. So homework will be due, so homeworks will be assigned on a day, and then they're due a week after in class. Just a reminder about the rule, if you do give your homework late that same day, which effectively means, that's my email, thank you for asking, let me just kill it. Uppa. No. Close tabs. Okay. So, just a reminder, if you do give your homework late, which will probably be applicable as the semester goes along, as long as I find it next day before I come into office, so you technically have till 9 a.m. next day, basically you'll get 10% points off. So whatever it is that you score, there will be a penalty of 10%, but it's better than not having turned homework at all. Okay? That clear? All right. So just have that in mind if you need it, but try to finish it on time. Or rather, this week you don't really have an excuse not to finish things on time again. Around midterms, then yes, it can get hectic. All right. So let's get back to our review of linear algebra. I hope most of this is boring and just a review of what you already know. But if not, there should be enough material for you to catch up. If you need to read, it's a chapter 8 in the textbook. And also there's, of course, slides provided. So we have defined vectors. What are vectors? What is a vector? When I say a vector, what do you picture? Nobody, everybody's like blank.
Force acting in a certain direction.
So force is a vector. Okay? So that's the one we can visualize easily. So the vectors up to 3 dimensions we can visualize. Okay? And the way we visualize them, so let's say that you have a force, what's important? You have force magnitude, okay? That's just how much force. So I'm standing on this ground, okay? And my weight, essentially, is times the gravity constant, is the force that I'm exerting on the ground. But that's actually if I'm standing upright, okay? If I'm standing in this direction, okay? Now there's a different pressure effectively that the ground feels under my weight because I have changed the direction of the force. Okay? So essentially, in every vector, it's important both the magnitude, and we're going to learn how to take a magnitude of any vector, whether it has 3 elements or 3,000 today. And you also have a direction. And the way we assign direction to vectors when we picture them, we start at 0, 0, 0, and draw a line directed to the point we're going to. So basically, in generally speaking, I could have 4 dimensions as well. So here are 2 vectors, okay, that have 4 elements. Those are hard to picture. I don't know how to really visualize 4 dimensions properly. Often, at least physically, we can do 3 dimensions changing in time. Okay, so you can have vector that is changing in time. The time can be the 4th dimension, but overall it's a difficult thing to picture. So essentially, you could have any number of elements, and then you can either tabulate them sort of as a row or as a column, and that is a vector. we have named all kinds of vectors that we have in petroleum engineering. Basically, the moment you have a data point for every depth, for instance, when you're doing logging measurements, you're going to have a vector of data, and we need to manipulate those, which is the reason why we're reviewing linear algebra. So we will first define a product, okay, of two vectors that basically takes two vectors and results in a scalar, and is going to be useful for different things. Now, here I say it must be a row vector times a column vector, and if I look at it as a matrix multiplication, which I will get to in a second, then basically row vector times a column vector is actually x1 times y1, x2 times y2, plus 3x3 plus y3, and I can keep going as many elements as I have. So it's really, I go to each spot, corresponding spots, I multiply those numbers, and I add all of those up, and that gives me a so-called inner product of two vectors, and the result of it is the scalar, just a number. That is actually useful. I will use inner products precisely in this, where my force is at an angle. Okay? I can take inner product of the vector in this direction and the ground direction, and I can get a projection out of it. Or rather, I can see, there's a formula, what would be the length, my length of me that I see on the ground projected. Okay. So inner product is useful in those cases. So the inner product is also sort of at the core of defining a vector magnitude or norm. And basically, if I take inner product of a vector with the same vector, just with the same numbers, maybe it's a row times a column, but I just take the same numbers and I transpose vector. Then if I take the square root of that, I'm going to get a norm or magnitude or a vector. Now, normally we're used to absolute values for scalars, right? If I have any, when I look at the speed itself, so I could have a velocity, which is a vector as well. Okay? But I'm often limiting speed in practice. Okay? I don't care whether I'm going 100 miles per hour in this direction, or rather, police doesn't care whether I'm going 100 miles in this direction or that direction. I'm speeding either way, so my speed is larger in magnitude than some given limit on the road, which is typically 65 around here, right? So basically that's my absolute value, and this norm of a vector is just basically a generalization of that, okay? Just for a table of numbers. So basically here's this is two dimensions just to have it easier to picture. So if I had a vector 3, 4 in 2 dimensions, you're also used to splitting it as 3 times I plus 4 times j, where I and j are unit vectors in x and y direction. Okay. So if this was my velocity, then square root of 3 squared plus 4 squared would be my speed. That's the actual length of this vector. So this is an example of a norm. So speed is the geometric length or magnitude of the velocity. It's formally also known Euclidean. So the regular geometry that we're used to is Euclidean geometry. It dates back to Euclid in Greek times. And formally it's also known L2 norm because I'm taking squares. So I could actually generalize that. So in 3D, I would just take as many vector elements as I have. So in any n number of dimensions, this would be the definition of this L2 norm, Euclidean norm, or sort of the norm as we are kind of used to it when we picture vectors and their lengths in 3 dimensions. I could also look at it as an inner product. So if I have a column vector x, then I take x transpose, which is just a row times a column So this is sort of a matrix way to define vector gravity. But this formula also works. Now the reason why it's referred to as a 2 norm is that I can technically generalize it, and I could have any p norm, and p is just a number. So if I had ones, so this is basically, I would take absolute value though, so that I don't have negative numbers cancel each other. So basically, this is L1 norm, is just the sum of absolute values. I have root 1, so there's no root. Okay. I could have had 3's here, and then I would take cubic roots and so forth. You can play with the norms as you wish. Okay, what's going on? I thought that I signed out of all of the. I thought, all right, should be good now. And then there's one more norm that we're going to call infinity norm, which simply takes the maximum. Fine, I can go on with definitions. They look abstract. Why do I need so many definitions? Let's put it this way. You have certain data, a log of porosity. So you have 100 porosities you're looking at. Sometimes you might be interested in maximum porosity of those. That's actually L infinity norm of that vector. Sometimes you're just kind of looking at the averages of the porosity, so you would sum absolute values of all of those and divide by 100 to get that average. So there are different situations where you're simply interested in looking at different things and you want different ways to measure things. What are you going to pick? That depends on what you want to look at. This is just the options that you might have, okay? In math, in general, you can just play for no reason whatsoever, but engineers typically have a reason, okay? And want certain options for a reason. So how about you all take a piece of paper and compute all 3 norms of this vector x is 1, 2. 3 norms being a 2 norm, 1 norm, and infinity norm. This funny number 8, by the way, is infinity, right? We know that.
Is it 1, 2?
1, 2?
Compute all the 3 norms.
Yes, for this vector. So L1, L2, and L infinity. What did you get for 2 norm? Square root of 5. So 2 norm is square root of 1 square plus 2 square, okay, which is square root of 5. What did you get for infinity norm? Infinity norm? It's the maximum between absolute value of the first. So this is definition of infinity norm. So here I have two values. So my x1 is 1 and x2 is 2. Maximum between 1 and 2 is maximum. Between 1
Three.
and 2.
It's
2.
two. Two. Oh yeah.
So if I had more, I would just keep going. It could be 100, right? So I'm just taking the maximum number of absolute values. Okay? So it's normal, like when you see the formula like this, you go like, it's actually just a cryptic way to write the maximum of all of the absolute values. And then what is my 1 norm? 3. So it's absolute 1 plus absolute 2, that is 3. Okay, so nothing special, it's just different ways to measure vectors. Here's an example from practice. Okay, so we're used to monitoring water in Austin. Okay, we get water from lakes around Austin that are created by dams. These are mostly artificial lakes. Okay, and we typically look at the aerial coverage and the depth of the lake. Essentially gives me how much water I have in there. So basically what's called stage 2 watering restrictions in Austin is when the combined storage levels of Lakes Travis and Buchanan drop below 900,000 acre feet. Okay? So acre feet is volume that makes sense for lakes. Okay? And basically you can actually go to LCRA, which is Lower Colorado River Authority, and they have daily monitors of levels in feet of all of the lakes if you want to look at them for some reason. Okay? So you sum those up, and then you know basically if you sum those up, what is the norm that I took? I have a vector of volumes in the lakes. If I'm summing up all of those volumes, which norm did I take of that vector? One. Absolute value, volume is positive to begin with. So basically, if somebody has programmed that, of course. Right? These alerts, they come as text messages these days to engineers who are working with, right? So there is a measurement device. That device reports the current depth that will essentially give the estimate of the volume. Okay? That gets logged into a vector, and the computer at whatever 6 a.m. every morning sums up all of those. And issues an alert is if alert is needed. So basically this class is about how do you learn to do that, right? How do you store your data in a way that you can process it with whatever algorithm and then create some sort of alert to anybody who is working with the data. Okay, so this is one way L1 norm is useful. There's another way that we don't think about often, but it's actually true. So normally when I think about distances, right? I'm going to say distance between me and you is, how many feet do we have here? Can you give me an estimate how many feet? 5? Let's say that it's 5. Is that really, if I'm walking to you, am I going to walk 5 feet? No obstacles in the way, right? So I gotta walk, well, quite a long time. So I've gotta walk on a grid. Okay. Now let's say that's typically called a grid of streets if they're regular, or a so-called Manhattan grid. So if you basically have something like this, so let's say that I'm a car driving, I gotta estimate how much gas I have to have, and your Google Maps have to estimate your actual distance that you're driving somewhere. So your distance is not this green line. That's for airplanes. If you have one, you actually have to do this or that, depending on traffic. Okay? So that's again L1 norm. I summed up my x1 absolute value and absolute of x2 if I'm in a two-dimensional space. So it's much more useful than you'd think actually at first. Whereas if you do the actual length here is 12 on this grid, whereas L2 would give you 8.5. Okay. You might run out of gas. Okay. So in other words, this is a lot of text just for you to have something to read from your notes. Different norms measure different things. It's also important to think about it in this way. When you look at this norm, L2 norm, it's going to take square of every value. So if I have values that are vastly different, like 0.1 and 100, okay? 0.1 squared will be 0.01. 100 squared will be 10,000. When I compare the two, I'm going to take it as 10,000. So I'm also almost going to forget one of these smaller values because I took the square of it. So sometimes when you're using L2 norm, it's going to play down smaller values compared to the large ones. Like, the large ones will kind of take over. And that's something important to think about. And if you want to just take the maximum, that's sort of the worst case scenario that you might have in certain situations. All right, so this is just a little fun. This is going a little more abstract. How many circles do you see? We see one for sure, right? Yeah. Do we see more? Well, if I'm asking, probably yes, but why? So if I take circle by definition is a geometrical location of all points that are fixed distance. If this is a circle of radius 1, it's a fixed distance 1 from the center, correct? Distance being measured in Euclidean norm. If I change the norm, then the geometrical location of points that are distance as measured by one norm away from the center looks like this. Let's take this point. This one's easy. This is 0 minus 1, correct? So this 0 minus 1, I'll point so that this is actually recorded. So this point 0 minus 1, its one norm is absolute of 0 plus absolute of 1, that's 1. Of minus 1, that's 1. Yes? So here I'm definitely at distance 1 from the center. How about here? This is 1/2 minus 1/2. Absolute value of 1/2 plus absolute value of minus 1/2 is still 1. So I'm at L1 norm 1 away from 0, and so forth. For every point on this graph, for every point on this line, this is line 1 minus x, really. Okay? So for every point on this line, I'm going to be at distance in norm 1 away from 0. So my circle in this norm looks like that. Same thing here in max norm. Okay? This is the point where all of my x2 values are minus 1. All the others are between minus 1 and 1. Therefore, in absolute sense, norm of all of these points is 1 for max norm. Same for this line, same for this line. So this is my circle okay, in max norm. Am I the only one who enjoyed this exercise? Yeah, I guess so. Never mind. Let's move on. So, I'm trying here, but yeah, I'm not well understood. So here's some properties of norms, just sort of formally. So norm of any vector is larger than 0. We defined it that way. So it's always positive number or 0. Basically, only a 0 vector in any norm has norm 0. So anything else has to have a norm different from 0. If I take norm of a scalar times a vector, it's the same as taking absolute value of that vector times the norm of the vector. And this is called so-called triangle inequality. Norm of, when I take a sum of two vectors, norm of that is always less than or equal to individual vectors when I take norms and sum them up of individual vectors. Okay. Now here's where actually scalar product, this U transpose V is actually a scalar product. comes into play in projecting vectors on other vectors. Okay? The angle between two vectors is defined as this is inner product of vectors u and v divided by their respective norms. We typically, for this is sort of a geometrical definition. We typically work with two norm in this. But formally, you could work in any norm, but it's most often worked in just the Euclidean distances, because then this angle is actually what we picture. I take two vectors in space, okay, 3D-dimensional space. If I take scalar or dot product between them, okay, and divide by norm of each vector, that will give me a cosine of the smaller angle between those two vectors. Okay. And I will also be often, if I'm just interested in direction, I can normalize the vector. Okay. So I will actually say that the vector has a magnitude of 1 if I just divide vector by its length, and then its norm will be 1. So these are the vectors that just define a direction of them. So this is so-called unit vector. I take the vector and I divide it by its length. Okay. Questions? Yes? No, so if this inner or dot product is a 0, okay, then the vectors are orthogonal. So, well, as a cue in, there's an exercise. So take U, and let's call this a V, 1 minus 1 and 1, 1. Are they orthogonal? Can you do that? Quick exercise. Can you draw it and convince yourself to draw these two vectors and convince yourself that they're orthogonal? So 1 minus 1 and 1, 1. Now, how would I normalize U? What would be a unit vector in the same direction as U? L2 norm, so U divided by square root of 1 plus 1. So it would be 1 over square root of 2 and 1 over square root of 2. It's essentially just a shorter vector in the same direction that has length 1. And this handwriting here is why I often use PowerPoint. You're going to have to endure some of my handwriting. But I try to minimize your exposure to my writing because it's not very pretty. Is everybody clear on how do I take unit vector? Okay. All right. Now we will just move on to matrices, which is basically stacking up a bunch of vectors. So normally we will denote them with the uppercase letters just to differentiate vectors and matrices. And you'll see when we get to MATLAB, the difference between matrix and vectors is really the number of rows or columns. Vector is essentially a simple matrix that has only one row or one column. Okay. So I can just stack up a bunch of rows and columns together, and that's going to be my matrix. Now, before I'm going to switch to some examples by hand, I just want to define. So just like in vectors, I'm going to sum up two matrices, only if they have the same dimensions, otherwise I cannot do it. Okay? And I will just go to corresponding positions and sum them up. If I wanted to multiply entire matrix by a scalar, I'm going to do so by multiplying every element of that matrix. Okay, so every element in every row and every column. And matrix transpose, just like in vectors, will sort of flip the matrix, so what was a row will become a column, and what was a column will become a row. So if I had a 3 by 2 matrix, it's going to become a 2 by 3. Okay? So that's just the definition, and we'll get to examples in a moment. And then we will also have to, though, come up with a more complex rule of how do I multiply matrices. So inner product of two vectors, but if I have two tables of numbers, that becomes more complex. Now, while I hook up my writing device that is different from the board, I'm going to ask you to come up with 2 by 3 matrix on your own and take a transpose. Yeah. And meanwhile, I will hook up a device that will project on the screen and therefore on the movie whatever it is that I write. And I will momentarily take this away. Is this getting projected? What is it? Okay, there we go. So what my laptop, unfortunately, is not a tablet, but I'm hooking up a tablet to it, and that tablet projects on the screen. Because it's projected on both my screen and yours, I can actually take a movie of whatever it is that I write, unlike this board. So this is why I'm choosing this tablet. So thanks for your patience. So what did you come up with as a 2 by 3 matrix?
1, 2 for the first row, 3, 4, 7, 5, 6,
That was simple, wasn't it? Okay. So this is my matrix A. And what we will, so number of rows here is how many? Is this what you wanted to write? So how many rows do I have? 3. And I have 2 columns, right? So these are columns. And these are rows. And in matrices, we will actually go in row by column in terms of dimensions. So this is going to be a 3 by 2 matrix. It's fine, we're going to work with it. Okay. Not a problem. So basically, this is number of rows and number of columns. So this is my dimension of this matrix is 3 by 2. Okay. Now if I flip it, I do a transpose of it. All I do is just I flip the 2, so A transpose. So my first row, 1, 2, will become first column. Second row, 3, 4, will become second column. And third row, 5, 6, will become third column. Same way, I can take a look and see that my first column, 1, 3, 5, has become the first row. And the second column, 2, 4, 6, has become the second row. Okay, so this is matrix transpose. Now, one important thing that I want to do with matrices, so just some examples, what would be 2 times A? Can I continue here? What would be 2 times A? For this example, yeah.
2, 4, 6, 8, 10,
2, 4, 6, 8, 10, 12. So this is essentially just multiplying every number with a scalar. And I could also do linear combination. I can do that if I have another matrix B of the same size. So what was your matrix? Same one?
Yeah.
Probably half of the class came up with 1, 2, 3, 4, 5, 6. Okay, then I'm gonna find. Does anybody come up with something else? There's one person. Woohoo! All right. So what was your matrix?
2, 1, 1, 3, 0, 2.
So I'm gonna say B is 2, 1, 1, 2, 0, 3. 1, 3, 0, 2. Okay. Whatever it is that I heard, it works. Okay. Now, so what would be then 2A plus 3B? It would be whatever I had for 2A plus 3B, which is 6, 3, 3, 9, 0, 6. And then I just sum those up. So all of the elements, I just sum them up. Can somebody help me up so that I wake you up here?
8, 7,
Any volunteers? Okay. 8, 9, 18. All right. Now, if I was going to be cryptic, so don't be afraid of cryptic, I would say, so let's call this C, okay? So this every element C, I'm going to refer to elements as Cij. This is element of C in row I and column J is equal to 2Aij plus 3Bij. Okay, so this is referring to row and column. I hope all of this is familiar. Okay, so then it's a boring review. Better boring than not at all. All right, now let's multiply matrices. Okay, so if I want to So let's say that I come up with, I'm gonna go with a small, 1, 2, 3, 4, 5, 6, those are gonna be large numbers, so I'm gonna just modify my A. I'm gonna change now, 1, 2, 0, minus 1, just to be a simpler one. What is the dimension of this matrix? 2 by 2. And I'm wondering, okay, what are the matrices or vectors that I can multiply this matrix with? So essentially, let's see. So I have 2 by 2. If I pair a vector, I'm going to call it x. That is 1, 3 here. Okay. The way I'm going to multiply is as follows. So this is my AX. I'm going to take first row of the matrix and this column vector x, okay, and put 1 times 1 plus 2 by 3 here. So this is essentially scalar product of the row of matrix A and this column x. So that's going to be my first element. And then I'm going to take the second row and multiply with the same column. So it's going to be 0 times 1 minus 1 times 3. So my result is minus 3 and 7. What I like on this tablet is easy play with color. So this is intuitive, all right, but if I wanted to define what can I actually multiply, so this is matrix vector multiplication. Can I multiply 1, 2, 0, minus 1 and just a vector that is 1 by 1, 7? No. Can I multiply, so that doesn't work. Can I multiply 7, 1, or 1, 1, 7? No. Dimensions don't match. Okay. So what do I have to have as a matching dimension? This is a 2 by 2. This is actually 2 by 1. Okay. So this so-called inner dimension, number of elements in this row, which is number of columns, and number of rows here, or number of elements in this vector, they have to match. Okay? Match. Otherwise, I cannot do this scalar product. Okay? So this is so-called inner dimensions have to match. Or else I cannot do the product. Okay? And then once they do, my result has dimensions 2 by 1. Okay? So very general, if I had matrix A and B, and this one is M by N, and this one is N by K, okay? So these inner dimensions are matching, okay? The result, let's call it C, okay? This is relatively visible on the screen, is M by K. Okay? So I did here an example with just multiplying a vector. If I had a matrix, so let's multiply this A with 1, 2, 0, minus 1, 1, 3, 0, 1, minus 1, 2. So basically this is my 2 by 2, this is my 2 by 3. The result will be 2 by 3. So I would just proceed basically column by column. So this multiplication with the first column we already did, it's 7 minus 3, right? That's the same thing here. And then the second one, I'm going to do 1, 2 times 0, 1 is what? 2. Then I'm going to do 0 minus 1 times 0, 1. That's 0 times 0 minus 1 times 1, negative 1. Then I'm going to do this first row, okay, with this column. What is the result? Minus 1 plus 4 is 3. Yes? So this is 1 times minus 1 plus 2 by 2. And then finally, do I have enough colors? This one times this one. That's 0 times minus 1 minus 2. Questions? It's a little too fast. A little. Should I repeat? So basically, I'm taking a row of matrix A and a column of B. So essentially, let's say this is row 1 and column 2. Then my resultant position 1, 2 is given by dot product of that row and the column. So basically, formally, if this is C, okay? So any element C, I, J, which is in ith row and jth column, is a dot product of ith row of A times jth column of B, and this meaning dot product. Scalar product, inner product. Those are all three names for the very same thing. So dot product, scalar product, inner product are all the same. And they're kind of equally used, so you kind of have to know. Have you done in one of your calculus classes this big sum thing? Okay. So I'm going to spook you a little more. If I had that notation, that my Cij is sum, okay? So I'm summing Ai, K, B, K, J, and K is from 1 to n. So that's actually a cryptic way to write down dot product of this ith row of A and kth row. So again, just don't get scared of the way this looks. It's basically just formalizing what this means. Now, the reason why I'm torturing you with something like this is that when I have things written like this, it becomes easier to program. Okay? You don't like it, but it's easier to instruct a computer to do. And you kind of, if you have matrices that are 1,000 by 1,000, you're very well motivated to instruct a computer to do it. Okay? So basically, the moment we have this formal sum, we're going to have an entire homework that we're going to be practicing these sums. Okay? For that reason, because then you can program better if you can formalize it better. All right, see you on Friday.